Right, so let's come back to equilibrium reactions. Okay, so we have A combining with B. Okay, so A is a chemical reacting with B. Now that is the first part. By second part, part of A will be gone, part of B will be gone, and then we have what? C and D forming, let's say 2C here. Okay, when they are formed, at this point, when part of this and that have reacted to produce this, when they form this, this also forms back, forms back B. So at every point in time, as A and B is forming C and D, C and D are also combining to form A and B. So at this point, we say the rate of forward reaction, this reaction going, okay, is equal to the rate at which the backwards reaction is also going. And then when the rates are equal, we say the system is in equilibrium. Okay, so let me say the system is in equilibrium because the rate of this adding to form C and D is the same at which C and D are reacting to form A and B. So we say they are equilibrium. Equilibrium means somehow balanced. Okay, and this kind of equilibrium, because it is going on, it's not stopping. Then we say it is what dynamic equilibrium. Dynamic changing in equilibrium. Okay. Alright, so that is how there is a definition. Now we are saying that we have a general rule that will transcend down the various formulas that we use. So let's, instead of making it A prime, B prime, what I'll do is that if we started with, let's say X amount of A and Y amount of B, we started with X amount of A, Y amount. When they start reacting, let's say when they started reacting, they produce n moles of at equilibrium. At the time you got to equilibrium, you had n moles of D in there. Because we have n moles of D in there, it's anytime n moles of D is formed, it means we should have 2n here. Okay, so what will happen here? For n moles of this to have formed, it means n moles of this, because it is 1:1, okay, n moles of that also reacted to form this, okay. So what will happen is it means we have to subtract this n from the X which was we started with, and then subtract this n also from because this happens, it means this is the n which has gone into producing it, okay. So this will be y minus n, okay. So this will become the equilibrium moles which will be reacting. The equilibrium moles which will be reacting, more or less the same as because they'll be in the same volume, you have a proportionate concentration to look at. Alright. Now the general rule is that at this equilibrium, at this point, the ratio of the product of the concentrations of the ratio of the product of the concentration of the product formed here over the concentration of the reactants raised to their respective stoichiometric numbers will always be equal to a constant, okay? Will always be equal to a constant. Let's say the K. This is what I mean. When you express this one, to the power 2. So this is the product. So this product. Okay. Over reactants. So the reactant we have what A. This is to the power because it's 1, here is 1, here is 1, but if it's 1 we don't write it. So that's it. So this is always a constant. Now the mass action is that these reactants, when we have expressed them as this, they tend to keep this constant. So the masses together tend to keep this constant. Okay, that means if you divide this one by this, you always get the same number, get the same constant, the same number, or the same number, right? But let's look at something briefly. When we do this expression, K is actually dependent on reactants that are able to move freely and interact, and usually it means it should be in the gaseous state or in the aqueous state. Okay, so it means those that we express in this equation must be in the gaseous or the aqueous state. If they are solid or liquid, they won't affect the dynamics of the equilibrium reaction. So they will be out if it's solid or liquid. They will not be. These are continuous. These are continuous. They are not separating to allow to contribute to the effect of reaction. So those that are moving freely, okay, they are interacting to form the reaction. So the reaction is not dependent on them, and that is why this K will be related to the substances in this state or that state. So if A is in aqueous state, let's say B is in aqueous state, this is also in aqueous state, this is also in aqueous, then we can express this one. But if A is, let's say, in solid state, B is in aqueous state, this is in solid, and this is in aqueous state, okay? Then A will go out, and then what D will go out, then we'll have this 2 giving us K. So that is one step. So the first step is what? It should be gases and aqueous. They will be part of this equation. The second step is the stoichiometric this is the stoichiometric value, okay? That's the value before the coefficient of the compounds, okay? It's what the exponent is raised. The exponent is what becomes the exponent, okay? So note that also the stoichiometric values become the exponents, okay? Right, so when you have satisfied these two conditions, then you can see that K is always constant, okay? Right, and this will apply in normal equilibrium reactions, solubility, and so on, okay? So we'll use this reaction to see how we can get the various equations. Right, so this one, so if you remember, when you're starting with something, this at equilibrium, amount of it would have reacted with this amount to form that. But of course, the ratio will be 1:1. So if you know one of them, you can do the subtraction to know what is left at equilibrium. What is left. So in this case here, if we are putting the values in, for instance, this would have been C is what? 2n. 2n. Because they are in the same volume, it's concentration, so it is this over the same volume, or over the same volume, okay? The same volume, so it should have been this over the volume that we have, okay? Then we'll raise it to what? Our power 2 here, and times D, which is what? D is what? D is n, so over s minus n over y minus n. So this will be so the value of n will be given to you, then you just put in the values. V will be the same, the value V will be the same, but because V will be the same, V will cancel out, so you just have to concentrate the number of moles in the equation. Okay, right. Now, so let's look at how this can be used for the various kind of equilibrium constants. So let's look at where we have, let's say we are looking at just normal equilibrium constant, normal equilibrium calculations, okay? Then K is equal to what? Let's say this is aqueous, this is aqueous. Let's make it aqueous. Aqueous. Let's make the this one also aqueous. And then this D, let's make these liquid. Okay. So from normal equation, normal solubility, so this is a constant, equilibrium constant. For equilibrium constant, okay, it's going to be what? Concentration of what? C okay, to the power 2. D is liquid, so we can put it there, over A, which is aqueous, so we can put it there. And B, which is also aqueous, so we can put it there. Okay? Right. So that is how it's going to be. Now, let's look at we put solubility here, so that we see how we can also use that as an equation. Right, so let's look at another one which we can use. Gases. Okay, the gases one. Right, so let's say for solubility, maybe you have NaCl. It dissolves this solid. Okay, this is solid. Then we put it in water. It dissolves and becomes Na aqueous plus Cl aqueous. Okay. Cl aqueous. Okay. The equilibrium constant for this will be K is equal to what? Product Na times what? Cl over. Remember this is solid, so we can write it so that you see that the equilibrium solubility constant, which is the same as equilibrium constant for solubility. When you are dealing with solubility, the equilibrium constant becomes solubility constant. Okay, this is general equilibrium constant. Okay? So instead of becoming over, this is solid, so we can put it there. So this becomes the equation. You get the point, right? For gases, let's say we have gas. Gas A plus B becomes C. Okay. Now, if we have something like that, let's see how to go. For instance, maybe this one is N, this one is H2, forming something like NH3. Okay, something like that. Let's see an example I'm giving. This is an example. Now, if we want to write, assuming we want to write, so there is something, an example I'm giving, okay? Right, so let's say we want to write the equilibrium constant for this. So the equilibrium constant for this Kc, then we're going to have what's concentration of C over concentration. This gas, this gas, this is gas. So because it's gas, you can put them in. Or with product over. But the ratio, let's say this, let me make this one. Let me make this one 2, so that you can see something here. Then you put 2 here. Okay, so these are gases. So this will be the equilibrium constant for it. Alright, so you see that this is how things will go. The equilibrium constant is the same expression. Okay, just that to change in small, but the same rule is applied. Okay, solid will not appear in the equation, so that's why we don't have over. Here, for all gases, so they all appear. Here, for this one, we said only D is liquid, so liquid will not appear. That is why we have this. Okay, so this is for this equation. Okay, this is for this equation, right? So this is how you can write it. Once you can write it, you read the question and put the values in, and then work it out to get your answer. Right, now the other thing I want us to look at is, which we are, so that we can exhaust. Let me put something here. And look at what you call the rate of reaction, and then we look at entropy, and then we look at the Gibbs free energy. Okay, so trying to put all the reactions together so that we have a very good we can bring everything down at the end of the discussion, so that we can look at the subsequent chapter. Alright, so let's see, for the rate of reaction, the rate of reaction will be how the product, let's say let me look at it, let's say for this reaction, we want to see how fast this reaction is going. That's the rate. Okay, you can choose any of the reactants or any of the products. First, you can choose a reactant and see how it is being consumed. It is being taken up. And then you can take a product and also see how it is being formed. Okay, and so the rate at which each of them is being formed will tell you can use only A. The rate at which A is being broken down will tell us something about the whole reaction. The rate at which this is being formed will tell us something about the whole reaction. So it can be the rate with respect to any of them. But if it is a reactant that you are doing, so it is being consumed, so the equation will become what? Negative. If it is product, it is being formed, so the equation will become what? Positive. So let's say with respect to A, then the rate of the reaction, the rate will be proportional to what? The concentration of what? A. That's what I want to do. Because if this A is small, then more reaction. If it is small reaction. So rate is directly proportional to this. Now the rate can be written as well, the rate at which A is changing with time. Okay, it's proportional to the concentration of A. This is the equation. Okay, right. Once we get this, let me put this here before. So that when we get there, we will not forget, we will discuss that. So this is the concept. So the rate at which this is formed, then is equal to that. Okay? Because this rate is the same as changing A over T. The rate at which A is changing with time. Okay, so we can rewrite this one as well. Changing A over dt is equal to K is constant. Once you know this, you bring equal to constant of proportionality as constant. Okay, so this is the equation. And then of course, once we know how to handle differential equations, we can easily say that the A is equal to K A dt. Now A is here, so let's bring A here too. If you bring A here, let me put it here so that we'll come back to it. If you bring A here, let's bring A here so that you have what? 1 over A, because it's multiplying. So it will come and divide that A. Okay, is equal to what? K T. Okay, so at this point we can integrate. We can integrate this part and then integrate that part. Okay, because we have with respect to A, we are integrating with respect to A here, and then we integrate here with respect to T. So this will become what? Ln A, the limit, okay? That's initial to final, okay? Because remember, when it is 1 over A, it's ln, it means it's ln. The answer becomes ln. From our differentiation, it becomes ln, okay? 1 over x, if you are asked to differentiate this, it becomes ln x. That is why this has become number. Then you put in the values, okay? It's equal to. If you integrate T, you get what? If you have 0T, because this is 0, okay, if you are integrating, you add what? This one to the power 1, add 1 here, what are you going to get? Your answer is going to come out as the first one that we did. So you're going to get your first equation as this. You can simplify this one as ln ln A. Let me clean this one so that you can have. Alright, so yeah, so let's put this one here. Let's assume, let me also make this portion, okay? Let's see. From here, let's put this one there. That is K is constant, so K is coming out. This is actually like saying the 1 T to the power 0, because this is 1 T to the power 0 T. Okay. Okay. Now I will leave this one here. I'll describe it later. Now let's see what is going to be the answer for this. So this is going to be, we add 1 to it, it's going to be 1 divided by 1. Okay, so that is going to be S T. KT as the answer. But remember, we said this is being broken down. If it is being broken down, then we are looking at a negative factor. It becomes negative. The other point is we will determine whether this one is a first order, second order, zeroth order, and so on. So let's assume we are looking at this one. So let's assume it is 0 order. That is, if this one is to the power 0, okay? Let's assume it is to the power 0. That means we are looking at it as being proportional to 0 in this case. Then we have this 0 here. Alright, so that is our final initial. Let's assume this is 0. Now if this is 0, of course any number raised to the power 0 becomes what? 0. Okay, so in that case we're going to have it coming to any number raised to the power 0, x to the power 0 is 1. So that will come to, so we'll come to the first one that we have a 0 here, counting power 4 as 1. Now if you look at it from that direction here, so you see that assuming if we have started from here and said this one was 0, it will be a different value if it was 1, 2. So this will be the 0 order reaction, this will be the first order, this will be the second order. Now we have assumed this is 1 in this case. This is 1. Okay. If we assume this is 1, let's see how the equation. So that at the end of the equation, you can also assume this is 0 or 2. And then you see that you get a different. So let's assume it is 1. In that case here, let's assume it is 1 that we are dealing with. Okay. So that one runs through. At the end, we're going to have the integration, because this is 1 over this. It becomes ln A, and it is of course initial to final. And then if you integrate this one, you're going to get that. We said we negate it because it is a consumption. Okay, so it is being reduced, so it becomes negative. So this will then eventually come out as that. Come out as what? Ln A concentration, which is let's say final over what? Because we're going to subtract it, it should be minus ln A initial, okay, the initial, okay, is equal to minus QAT, okay. This is minus, so it can be written as ln A over initial, okay, or not, is equal to what? Minus AT. Okay, so this can be an expression for first order. That's when we have chosen this one to be to the power 1. Okay. Now if you put it to the power 0, let's see. So this is the answer. This is the answer for first order. Let's see if you put to the power 0 here, what do you think will happen? This becomes 1. This will be 1. Okay, in that case, if this is 1, t multiplies it, this will be 1. Okay, and you won't get the fraction form here, so that will be kind of a straight. Well, let me just work that one through so that we get that. So this is first order, what we are getting. Now let's assume the rate is to the power 1 here, to the power 0, that is the 0 order. Okay, so from here we would have gotten what? The A dt is equal to what? K. This is to the power 0. Any number to the power 0 is 1, so times 1, which means K becomes what? 1. And then this would mean we can send this one there, so that we have the A, change in A is equal to K dt. We can then integrate this and integrate that. This is if you integrate this part, what are you going to get? You're going to get A final, and then initial is equal to KT, which is also going to be what? Of course, we said it's consumption, so let's make it negative straight away. KT. You can actually make your negative from this point. Okay. So KT, right? So this is going to be what? A final minus what? A initial is equal to minus KT. Okay. So we can say your A final is equal to what? A initial minus what? KT. Okay. Right. So this is constant. This is constant. Okay. This the T, and these are the concentrations. So this can give you the expression for the 0 order. So you can relate this one to like saying y is equal to what? This is constant, initial is constant C, Plus what? K is the gradient x. So you have this kind of equation. Okay, this actually the m becomes a negative k. Okay, so this is that linear equation. You can also try it when you make this one. So you can try the Lewis equations once you know you how to integrate. Okay, so you can put, let's say, you can put to the power 2 here. Let's see what happens. Put to the power 2 here. What are we going to get? We're going to get what? dA over dt is proportional to negative k, because it's reducing, the reaction is increasing, this is decreasing, so let's put it negative k what? A to the power 2, right? Which will become what? We can bring a here, because we have a, we bring a here, SMT there, so to be a is equal to negative k a squared this comes with times what? dt. Now let's bring this one to this side. It is multiplying, so it becomes a divide, so we have what? 1 over a squared a equal to negative k dt. Okay, now because we have this and that, you can integrate with respect to a, the same thing. You can integrate this one to on this side with respect to t. So if you integrate this side, if you are integrating this side, what I'm going to get is like you have what? 1 over s squared. When you have 1 over s squared, you just use the same principle like we said. You try to see if you remember the first one. Right, so when you have this, okay, this can be written as what? X to the power negative 2. And if you can integrate this one easily. Okay, if you integrate, you just add plus 1 to it, it will become x minus 1. Then divide by what you got, minus 1. So you see that this is going to become what? Negative a to the power minus 1. Of course, we will integrate from, we'll have to integrate from where? From initial to final. It's going to negative k t. Okay? So from here, so let's say this is the final. Going to this final. There's a final one. Because it's minus 1 to the power 1, we have to put it in. Okay? There's a final one we're putting. Minus the initial. The initial is also going to give us this. It's going to be minus. Okay? It's minus, so it becomes what? Plus here. Because this is what we have. We put it there. Then put in y2 and then count subtract. So if it's going to minus, it becomes plus. And it's going to be a initial. Okay? This is also minus 1. This is the a final. Okay? Is equal to minus kt. So this becomes the expression that we are getting. Okay. Now you can rearrange this one and say, you can rearrange this one and say what? A not 1 minus a negative 1 f. Okay, is equal to minus a t. Alright, so this becomes the final thing that you have to do. Okay, so this you can rearrange. You can send this one there. Okay, you're going to get what? It's equal to what? It's equal to, sorry, minus 80. Okay, you can rearrange it like that, and that becomes the final equation. So you can go on and on depending on which order that you are given. Okay, so the order is telling you how the rate relates to the concentration. So let's say the rate of this reaction in relation to A is the zero order. In relation to A is the first order. That will be provided. Okay, maybe in relation to C it is a certain order. because the rate of reaction will depend on each other at a certain, it will depend on each component at a certain factor, okay, and that is the factor you put in here. And you can use that. Once you get the equation, you can go through the process and then derive the final equation, right? Okay, so that is for the rate. So you see that the rate of the reaction doesn't depend on the mole ratios. It has a certain value. It depends on certain value. Maybe the rate it is measured from the chemical reactions that are done. Okay, and then you can tell how the whole reaction depends on A. The whole reaction depends on that. Okay, so among these, sometimes we need a certain energy level to be able to let the process start. So we have certain steps which are rate determining step. That means that step is when it is when that particular step is overcome, then the reaction goes on smoothly. Okay, that part becomes more or less the rate determining step. Okay, right. So this is for rate of reaction, how to derive the equation. Once you can derive the equation, the initial amount will be given to you, final amount or whatever, you will be asked to find the final amount or find time t and so on. So you can manipulate the equations in the question. Alright. So that is for rate. Okay, so let's move on. So we have solved that part of the rate. Entropy was here, so let me put entropy so that we don't forget to discuss it. Alright, so we have finished with rate. We've discussed equilibrium constant, solubility, product. Remember, solubility product is not the same as solubility. Solubility will be an amount in a certain mole, okay? The amount of the substance in a certain mole, that will be the solubility, okay? It is so at a certain temperature, okay? But this is solubility product, so it's a constant, that's a constant. So we'll read the question, it is solubility, interpret it. It tells you that the solubility, let's say solubility of sodium is 2 moles per whatever, but then it means sodium here, we have 2 moles of it in that solution. Okay, so that will let you, if this is 2, then of course this is 2. It helps you to work out the product. Okay, so the solubility is given to you so that you can work out the solubility product. Okay, now this is gas. Okay, that's the gas part, it's the same thing. We have said the reaction will depend on aqueous state and then gaseous state. Okay, so this is the gas form. Now, just on the gas form, let's talk briefly about how temperature, pressure, and volume will affect equilibrium reaction. Okay, this equilibrium goes back and forth. Okay? So what will happen is, according to Le-Chatelet's principle, okay, when you put in stress in this system,